So yeah, thank you for joining this session where I will show you the basics of the MicroStream framework so that you can access your data much faster than with the traditional approach. The traditional approach, we all know, we have the Java program running in memory, we have objects with data and programming. But if we need to access the data, then that's stored outside. We need a database most of the time with tables, etc. And that's probably because databases are older than Java. So the moment that we started creating Java applications, we have already data in the databases. But retrieving data from those systems, any kind of external system, basically, I will focus today on the databases and Hibernate of a way of retrieving the data, but actually it goes for all kinds of external access that is rather slow and involves a lot of development, a lot of tuning, and a lot of headaches. So maybe there is a better solution which can be offered by MicroStream. I'm Rudy De Busscher and I'm developer advocate at MicroStream, but I'm also working with the micro profile specifications and the Jakarta specifications and also include implementations of MicroStream in those two products. Data is everywhere. Maybe there are a few exceptions where you have an application that retrieves data from external sources and aggregates them or transforms them and returns them to the user. But basically every application has data. Every enterprise application has data from web shops, the products and shopping baskets, through manufacturing situations where you have the orders, the planning, etc. You have healthcare data, you have IoT data. Data is everywhere. And that also means that a lot of solutions were developed for storing those data. If there is a site where they try to list all the possible data storage ways, and that means databases, different databases, but also NoSQL solutions and in-memory data grids, etc. And you can find there more than 300 different solutions, because each of them has pro and contra. Some of those solutions, like for instance, the graph databases have specific functionality specific for that kind of problems, but there are a lot of different possibilities, because there is always something that can be done different and especially for a certain situation, so there is no general solution. And the same is for the Java world. We have, as I said, our object graph, which is running there, which is retrieving data from the database, but it can be a NoSQL solution like a key value store, or retrieving it in a JSON format, that graph database that I mentioned, or on the bottom left, you see there the in-memory databases and the clustered solutions. But all of them have two things in common. First of all, they are externally to our Java process. So that means that if we need to access the data, we always have that latency. We also need to get the data, retrieve them, and that takes some time. Even if it's a simple, small data value that we retrieve, it always takes the additional time of traversing the network and getting the data back. But we also have that there depicted in the slide with that red block. We have a rather large thing around data conversion and typical within Hibernate and the JPA solution, that object relational mapping. Because we retrieve data, pure values and numbers and text and dates most of the time from that external system, we need to convert them back to what we are used to working with in Java, objects. So we need to have some mapping from those values like price and number quantity to a real order object in Java. those two things are common for all solutions and are also the cause of the many problems that we see within the applications in those traditional applications. Because if we have a rather quick look at how you access the data, then you see that there are a lot of steps that need to be done. First of all, there is a query written in Hibernate query language or JPA query language, which is actually a query based on objects, not on your database tables, but it is on objects within the JVM. So that needs to be parsed, that needs to be verified, understood what you actually want to have as the result of your query. And then there is always a check if that data of that information is not already available in the cache. With the JPA specification, there are explicitly mentioning of two caches at the first level cache and the second level cache. So that means that they realize that data retrieval can be an issue, can be slow. So we need a caching solution. So even there you see that that retrieving data gives you some problems, will have some additional tuning sessions required, etc. One of the things that you can have is that, for instance, if you converted your query to that JDBC call, that you have the classic n+1 select issue. For instance, if you select with one query 100 records, that you issue 101 queries to the database because it needs to retrieve some additional data for each record that you have selected. So that can be an issue. That there are tools to find it, but again, it takes some time, it takes some expertise. The execution of the database queries can also be an issue at the database level itself, that you can have slow queries due to indexes, how the data is structured, for example, but also by some misconfiguration or things that are not updated correctly, like, for instance, the table statistics. If the database thinks that there are only 5 records in the database, in that table, sorry, and you perform a query, and so then he decides to scan the entire table instead of using indexes. But what happens if there are 1 million records in the table instead of 5 as the statistics says? So that means that you have a very slow query. And as I mentioned, once you have those values like numbers and text fields, etc., you need to even convert it to objects and then update the cache or statistics, etc. So there are a lot of things that needs to be done for retrieving data, database-wise, but also the other systems like NoSQL and the other solutions that are available that I mentioned that are on the website, those 300 possible cases where you can choose from. If you want to know more about that, then you can look up a lot on the internet around this problem. It's called the impedance mismatch, the difference between the object relational world and the Java, and that's so between the Java world and the database world. So you can read more there, and you read all about those different kinds of mismatches. But what if we start thinking differently about our data? What if we say, well, we have already Java instances in our in the memory available. We have, for instance, an order. What if we say that that instance is the primary data source of our application? So it is not just a representation of the data that we have stored and retrieved from elsewhere, but the JVM memory itself is the primary data source. So data is part of our application. And that has some very far-going consequences. Because if you say that all your data is just in Java objects, then the only thing that you need to do to retrieve them through queries is writing is accessing getters using the Stream API, etc., which is ultra fast. You don't need any conversion, so that's basically instantly. You also don't need to learn all those functionality of the frameworks like Hibernate or how to access the NoSQL solution, etc. So it is also not only at runtime beneficial, but also for the developer productivity, you can develop much faster. Because I hope I can say that we all know Java very well, so we just can use Java and that's it. We don't need to use any other solution, any other framework. Data in the JVM, of course, does not survive a process restart. So that's why MicroStream, and that's also the reason why we have MicroStream, because reading the data, you don't need MicroStream for that. But saving those data and loading it at process start, that requires then the Java serialization engine we have within MicroStream. It's not the Java one, the standard Java one, which requires, for example, the implement serializable, because that would put some constraints on which objects you can use in your memory as a database. No, we created something entirely new from scratch, which can represent your Java objects in a binary format, so that it can survive a process restart. And then instead of doing all those steps, as we went through in one of the slides, there is only one simple, fast step: select within your JVM. And that's the way how you select your data. Later more with some examples and some graphs to see how fast it can be. So instead of having a different representation of your data outside of your Java process, we can actually store an object graph, so an interconnected set of Java instances in a binary format externally. It can be on disk, it can be as a blob in a database, it can be as a blob in a distributed cache or event streaming or any kind of other solution. So it is much easier, so that thick red block there of conversions and etc. is now only a small layer of the MicroStream framework. Because as a developer, most of the time you're only confronted with, let's say, 3 to 5 classes and like 10 different methods that you need to know of MicroStream. I show you in the demo. It takes about 15 minutes for a few demos. Well, in those 15 minutes, you basically get everything you need to know to get started with MicroStream. So it is a simple solution with not that much concepts, and it will give you access to your data extremely fast. I mentioned the demo, so let's get to it then, of course. If there are any questions, yeah, please put them in the chat. I can answer them at the end. So I have here a Java program, a Maven program, a Maven build setup. I'm using JDK 11. Hopefully everyone by now can use JDK 11, but version 7.1, which was released last week of MicroStream, also support JDK 1.8 in case you're still on that version. You need one single dependency, so there is no external process running that's keeping track of your data. It is just some classes, some code that is added to your application itself. And except for that SLF4J logging API, there are no other external dependencies that are pulled in transitively. So that means that there will be no conflicts with any kind of other framework library that you like to use. And it's very clean. You will not have those dependency hell as you sometimes have with Maven and other frameworks. For the Hello World, show you a few things here in Hello World. First is the configuration, and secondly is how that you store data to an external storage. So for the configuration, you can have a limited, a very basic configuration. We will see more of configuration options in the second example. But in the first one here, we only need to configure two things, which is saying the root object, what is the root object for MicroStream, so that it knows which object graph it needs to operate on. And the second is where is the binary representation stored. In this case, it is stored on disk in a directory called data. That root object is a POJO. So there are no interfaces, there are no annotations. Every Java object, be it from standard Java, with strings and list, or your own products here, which is also just a plain POJO, or even any kind of third-party Java class that you bring in with your dependencies, that all those can be handled by the storage manager. You don't need to do anything specific. Just the object is enough. It finds out what the values are that needs to be stored in that external system. When we start the object manager also, then we read the data, which are stored from a previous run. Here in this case, it is empty. You see there is no data directory here, which will appear in a moment. So it is empty. So printing out the roots will just print out 2 times NOLL, once for the timestamp, then once for the list of products that we have here. We can set the timestamp. That's just a quick and dirty way, let's say, to put some timestamp there. And if there are no products, as in we have the case now, we add there 4 products and we say store me these informations, these data, store the entire root. This store root is only needed the first time, so when the database is empty, so that everything is stored. So that means that our timestamp is stored and the product list is stored. So we can run that program already. It will be empty as a data, and it saves then the timestamp and the product list. And you see appear here a data directory with the data, as I said, in binary format. So you cannot make a lot of sense out of that data, but MicroStream can perfectly handle that. If we now run the second time, we will see that the root does contain our 4 products that we have added and the timestamp. We set it again, but it will not store it. I will tell you in a moment why. Because we see that there are 4 products, so we add a 5th one, and the other rule of MicroStream is that you should only store what is changed. So what do we change here? Well, that is this list of products. So we store this list of products. Then he will figure it out, MicroStream will figure it out what is changed, and it will find out that there is a 5th product added, and he stores only that changed entry, not the 4 products, which were there already. But that also means that the timestamp, which is not part of that list here, is not stored, and we will not see it. So the second run will show that the timestamp was successfully stored and that we have those 4 products, and we have now added a 5th one. We can see that if we run it again in a moment, but first say what we will do in that next run. We will change 1 product, because the 5th product that we added now, I added the pizza as product, which I labeled as entertainment, which is good, but I want to change it to food. And again, we change what is stored. This time we changed the product instance itself, so we only need to change the we need to store the product reference here. If we would store the list again, then this change would not be processed, because he sees that the list itself has still the same 5 references than when you loaded it, so it does not change them, and it stops there. So we actually need to change the store what is changed. That's basically not that much different from what we do with a database, for example. if you want to update something in the database because an order is changed, you make sure that you launch an update statement for that order. So here also update what is changed and you're good. So this time we run it. It was 16:18 before, so although we are now 2 minutes later, it is still the same timestamp because it is not saved, but we have now our entertainment as a product pizza as entertainment, which is changed now to food by this run. So if we run it again, we see that timestamp is still the same, but we have now the correct product type here. So this shows two important things at that root concept, basic configuration, where you what as a minimum you need to specify the two things there, and the important concept of storing something. Configuration is a bit more elaborated. You can do a lot more. For instance, you can define all the different aspects of the config of the storage channel and where it is stored, etc. We have a term for that. We use classes with the term foundation, which are actually some kind of builders, builder classes, where you can define every aspect of the configuration of MicroStream. In general, MicroStream consists about, I think, around 20 different sub-modules, subsystems. They are all an interface, so you can swap out the default version and use your own version or an adapted version or whatever. For the configuration is that here by default, we have that abstract file system, so that we can write to different kind of targets like the database, like Kafka or cloud storage like AWS S3. And the non-blocking IO file system is then the version that writes to a data file. So the long version of just saying the data needs to be put there in this directory is by using this construct of the builder here. But we can also define the number of channels. The channel is the thread that writes the data and reads the data to disk, for instance. If you have a lot of data or you need to process a lot of data, it is good that you increase the channel count from 1 to 4, for instance, so that there are more objects processed in parallel, so that means it goes faster. You can set up a backup instead of just relying on that one storage system. You can send it also to another one, here another directory, but that can be an entirely other system. That can be as long as it is sent somewhere. It does not need to be the same type, so it does not need to be a directory here. It could be a database or something else. But with that foundation, that builder, you can define other functionality. For instance, define the class loader, which you probably need to do in application runtimes due to the differences in class loaders. You can configure specialized handlers. For instance, for JDK 17, there are a few new types that are introduced there that require some optimized handlers internally. So that's the way how you can set them all on this foundation and then create the storage manager from the entire config that you made here. Let's see, there is a question. So can I show them? Yeah, how can MicroStream handle big data sets? I'm coming to that in a moment. So that will be next. You don't need to do everything in code programmatically. You can also use, for instance, property files. So this is the one that is using the database. So for that, you need some additional config dependencies. You need the SQL version of the abstract file system. That's for the database, and then of course you need the Postgres, the driver in this case, but you also need this dependency at the embedded configuration dependency, which then adds the functionality for reading the configuration from a property files like this. This is all described in our documentation, what all these keys are, how they are called. And this means define the storage file system as the SQL one, and define the abstract file system as the SQL one. This is just a name that you can provide for your own clarity. And then these password, user, and URL are actually used by this data source provider. So every time you add the MicroStream wants to connect to that database or need to connect to the database, it will call this method so that you can provide the connection. It can be just a simple data source where you hard code, not hard code, where you just read the URL, user, and password, but you can also retrieve it from a connection pool or whatever. That's depending on the environment where you run it. The last example that I show you is how to use AWS S3. There we have that blob storage file system where we get a standard a S3 client where we where based on the credentials we have. So these are fake, obviously. I would otherwise not show them. An access key and a secret key. You create that client. And then again, you have that simple possibility to just specify the root and the file system, which is then now AWS S3 based one, where you define the bucket name here as the directory name. I see there was a message, a request around Neo4j. Is Neo4j supported out of the box? I don't think so. We don't have that one. But again, if we would use Neo4j, it would just store the data as a blob. So we are never using the, let's call it, native capabilities of the system. Like if we store it in a database, it is also as a blob. It's just a meaningless set of bits and bytes for the database. We just use it as a dumping ground for when your process can start again. That's the configuration one. So that's probably the most elaborate system that you need to learn. But still, you see, it's rather simple. It's always the same structure. There was the question of big data sets, and there we have the support of support for reading those big data sets with the usage of what we call the lazy concept. Because, as I said, when the storage manager starts, you always get all data loaded into memory. But of course, if you are having terabytes of data, that would be a problem. Here I have an example where I have 2.8 million records, which is already a rather large data set. Of course, it's not terabytes. And instead of loading them at start, we use them in a root, which is a map, where we have a lazy list of the data. So instead of loading all the data at startup, we only load the map structure itself, but not the values, because we only have one instance of lazy, and that's not actually containing our data. Because from the lazy, we have a get method, or peek if you don't want to load it if it's not available in the memory. With get, you actually load it from memory or from the storage if it's not available. And it's all, you can also clear it immediately. So this example, it loads the data for day one, which insert it on the disk, and we see how much time it takes. We do a few other loads, and then we load the data for day one again. And then you will see that it is, of course, instantly instead of retrieving it from the disk. So let me open this one a bit more. So loading for day one is around 93,000 records, and it takes about 1.3 seconds now. It's slower because I'm doing screen sharing, because otherwise it is less than 1 second. Actually, there was also a garbage collection going on at the same time. So because you see, I have even more free memory after I've loaded the data from the database. But that's coincidence, because when I load 3 more days, it goes down as it should be. But accessing it the second time, the time goes to 0. Because yeah, just accessing a list from my memory takes a few nanoseconds, so that's not showing up in this millisecond range. So as concepts, you only need to learn a bit about the configuration to use that store method and the lazy, and for the rest it is just standard Java concepts like objects, statements, stream, API, etc. So no longer put a few things on the right there about all those specific things for databases like queries, indexes, data manipulation, language, pooling, whatever, annotations, inheritance, strategies. Just plain, simple, easy Java, and it works fast, as you will see in a moment. It's the summary of that abstract file system. The storage manager used 1 or multiple channels. In each channel, there is that serializer that converts the Java instances to and from the binary format, and you have several implementations so that we can store it on disk, database, or Kafka, S3, as we have seen, etc. And the lazy one, which is basically built on top of weak references. So that means that if the garbage collector of the JVM sees that there is need for more memory, it can just throw it out. Within the version 7.1, we also activated our own garbage collector, the MicroStream garbage collector, that even before the memory is full, that it starts throwing out lazy references which you did not access recently, so it preemptively makes sure that you are not running out of memory due to those weak references and that lazy implementation. What I have told you up until now is all functionalities available in that open source version. You can just find that in the GitHub account in Maven Central, is for a single JVM. So clustering is possible to do it, but you have to do it manually. More on that in a moment for a proper clustering and a cloud solution version. Within that open source version, you have that the com channel class, which is using the asynchronous sockets that are available in the JVM. So with that, you can create your own clustering solution. The downside is that you have to do it yourself as some manual codings. For instance, you can create that server which is connected to that com channel to your application, which can be running multiple times. And either the server or the client, if they put something on the channel, an object, for instance, then the other side can just take that object from the channel in a deserialized format. And it works. You saw there the GitHub link to the repository where I'm now showing you the example running. So here on the left, bottom left, we have that server, which is just a simple jar file which listens for connections from, for instance, the first instance, which is running on port 8080, or the second instance, which is running on port 8181, both small applications running on Payara Micro, but it does not matter, it's just using standard Java SE. So if we then curl that first instance at the endpoint for the products, then it asks the server what is the list of products, because it was in the first one, so we get that there is one product called banana, and it retrieves it from the server. Same for the second instance, port 81, and we get the result back again of that same product. If we post it to the second instance, so post 8181, a new product, an apple, then the client sends it to the server, and the server broadcasts it to every other instance. So that means if we ask the products now from that on that first instance, we see that we have both products there. So there is a synchronization possible. You can create your own clustering solution. You can do your you can roll out your own solution, but it needs a bit of work. A more proper solution is, of course, is the MicroStream Cloud called as something new, which we are more or less launching it now this week during JCON, which is an enterprise-based solution where you use Kafka as a storage, and you only have to interact with the storage manager, but you can create there an entire clustering solution. If I'm correct, on Thursday, there is a session where this entire MicroStream Cloud is presented in detail. I promised some numbers to show you that it is really faster than a database. You see again there the GitHub repo where you can have a look at it. You can play with the examples, so you can compare in that case MicroStream with JDBC and Hibernate. Instead of Hibernate, you could take any kind of other framework, Eclipse Link or JOOQ, Query DSL or whatever. We just took Hibernate because it's the most popular one, and basically all those frameworks are comparable, and my MicroStream is a lot faster than the rest. I mentioned already that example with 2.8 million records. That's from this write performance test to see how fast can we store those records. So the load scenario just loads the data from the CSV file and does not do anything more. So that's to have a reference. It takes around 8 seconds. MicroStream then needs an additional 40 seconds to store them on disk. That's quite some time. It's just on my machine here, so it is not something specific as a server. So only the comparison is important here. Because if you see, if you're using JDBC to store it in a Postgres database or Hibernate, then it is 94 or 116 seconds more to store those 2.8 million records. Main factors here for that additional delay is, as I said, you have the latency to send it to an external system. And in this case, checking if the primary key value, if it's unique. So every time you insert records, the database need to check that if that's unique. That's also happening within MicroStream, and you can create a hash table or a set to make it unique. So you can have that same kind of functionality, but Java will be faster there, than still faster because you don't have that latency. So MicroStream will be faster. Reading then, that the previous one was a write example. So reading, we have a simple query where we just read from a table. In this case, it is the customer table. If you go to the bookstore example, which I reworked for this performance test. And we do some kind of paged loading. So we load the first 100 records, then the next 100, etc. And so we do that 3 times. And here also there is a faster access. MicroStream, and the bar is longer because, yeah, you also need to load and connect. The green blocks are loading the data in case of MicroStream, or yeah, in the case of JDBC, you need to connect to the database, and Hibernate is connecting plus initialization of Hibernate system itself. But once the system is ready, so you only need to initialize it for the first time, you see the blue blocks, then querying the data with MicroStream is only 20 milliseconds, JDBC is 130, Hibernate 140, so they are comparable. So that means that reading with that customer table through MicroStream takes 7 times less time than the traditional approach with Hibernate. It can be even better if you go to much more complex queries. Here we have complex queries with multiple tables joined, where we have on one of those deeply nested tables, we have condition set, etc. And as an additional thing to make the comparison a bit more fair, for MicroStream, we use there also the lazy loading. So as part of the query, MicroStream will load data lazily. These are then the results in a graph. So again, you see the same green blocks, the initial loading of MicroStream or the connecting, but you see the query time. The first time for MicroStream is still, it is still, you still see the block size, so it is not 0 milliseconds, because there he does the lazy loading as part of the query itself. But the JDBC and Hibernate takes around 700 times more before we have the data. So if you see there the on the slide the timings for the second time, so no lazy loading, and for JDBC and Hibernate you still need to load the data. That means that it's much faster. So I think we can say that MicroStream is working at light speed. We cannot go any faster because we are at the limits of the JVM can go, because we are using pure Java constructs. So then you may be asked, what are some use cases? Where can I use MicroStream? Well, anything for anything. The only limitation is probably your imagination. But we see 3 typical use cases: the local cache for microservice environment, serverless, and offline storage for mobile development. Quickly going over them, for microservices environments there, because you have only that one single responsibility, you in order to respond to a request from the user, you probably need to contact a lot of microservices, so that takes time, again, due to that latency. So that means that people are now starting creating caches locally for them, so that it goes faster. For those caches, MicroStream is ideal because it is available very fast. It can be updated by some events stream system when there are changes done in the environment or in the system elsewhere by microservices. And even if you restart your process, your cache is still filled with data from the previous run. So it is a hot cache, as they call it. Serverless, as you have seen in the Adam Bean keynote, serverless is maybe becoming the way to go for a lot of projects. And with that lazy loading functionality, we load some standard basic data at startup, but then we do the lazy loading. And as we have seen in that complex query, that is even much faster than the database. And the added advantage is that instead of most of the time a rather expensive cloud storage, a cloud database, you can use something like an S3 bucket to store your data, which is very cheap. For the mobile development, because Java is MicroStream is not only limited to Java, but you can then also develop for mobile devices. For the offline first strategy, there where the UI stores, instead of using SQLite, it can use MicroStream to store the data locally and later do a sync when they are the person is online. As I mentioned, not only Java, you can use it also with Kotlin, Scala, Groovy, or whatever. As long as it is Java based, you can use it. It runs everywhere. There is everywhere where Java runs. container, a microservice, a monolith, that's no problem. And as of now, we have a lot of supported storages from databases to NoSQL and cloud storages, and even you can write your own implementation by implementing that abstract file system. There are you can use it the Java the MicroStream code pure. You just integrate it within your application, and you can use it in any kind of framework. But it is by default integrated within Helidon. So if you have Helidon, then you have automatically also MicroStream available as module, so you can use it immediately. Also, it is integrated within Micronaut, the same there. And there are also specific integrations developed for Jakarta EE and Spring Boot, and there is also one for Quarkus, which will be released later because that requires as a minimum JDK 11. Those integrations, it makes it easier to configure it and to, for instance, expose your root object as a CDI or a Spring Bean, for example. More info for those that did not found it yet. We have a website, we have our GitHub repo, and you can ask questions on Stack Overflow. I have seen that Marcus already did a good thing in answering some questions, so I'm not sure if there are still some other questions which are unanswered, or if you have any other question which pops up your mind for the moment. Yeah, so I think they are all answered for the moment. So then I can just say thank you for joining me, and I hope you enjoy the rest of the presentations for the rest of the day and the next days on the JCON conference.